Good afternoon, student. Today we will study the particle in rectangular three-dimensional box. This is the applications of the Schrödinger time independent wave equations. For this, we consider the free particle of mass m be in motion in a rectangular potential box with a side of length ABC. Here ABC to the XYZ axis. A along the x axis, B along the y axis, and C along the z axis as shown in the figure. And let psi x is the wave function associated with this particle. Then the particle is free inside the box. Here the particle is free inside the box. That is, there is no force acting on it, so that the potential on this particle is 0. Thus the wave function is psi x y z. That wave function is along the x axis, y axis, and z axis. Therefore it is defined as psi x y z equal to 0. That psi function is equal to 0 when it is outside the box. Therefore for this we write these conditions: when the x is less than equal to or less than equal to 0 or greater than equal to a, then it becomes 0, means outside that outside that box along the x axis. Similarly, psi xyz equal to 0 along the y axis when it is outside this box. Therefore we write this limit: y is less than or equal to 0 or greater than equal to b, means here. Similarly, if particle is here, means outside the box, then the psi function become 0. Similarly, the potential energy means V x y z equal to 0. Here inside the box this particle is free particle. Therefore the potential is, therefore the no force is acting on this, and therefore the potential is 0 inside the box. Therefore we write this V x y z equal to 0 inside the box, and that Vxyz is equal to infinity, means outside this box along the xyz axis it become the infinity. Here we write this condition here: inside and outside the box along the xyz axis. Then consider the Schrödinger time independent wave equation for the motion of the particle inside the box is delta square psi plus 2m upon h cross square in bracket e minus v x y z bracket close psi equal to 0. Now for free particle this v x y z equal to 0, means potential becomes 0 inside the box. Then we can write this equation like this: delta square psi plus 2m upon h cross square e into psi equal to 0. This delta is nothing but the del square by del x square, del square by del y square, and del square by del z square, and then multiply by psi we get del square by del square psi into upon del x square plus del square psi upon del y square plus del square psi upon del z square plus this term 2me upon h cross square into psi equal to 0. This is the equation number 1, and this equation number 1 is called as the differential equation for the wave function psi. The wave function psi xyz can be assumed to be the product of three functions. Here this is the wave function, and here in a three-dimensional box we consider that wave function is the product of the three functions, means x, y, z, and thus we can write the wave function psi x, y, z equal to, here this wave function x, y, z is can be written as x is the function of small x, y is the function of small y, and z is the function of small z, which is the equation number 2. Using this equation in equation 1, here we get the equation 1. This is the equation number 1, and then define the psi function is a product of x, y, z. Then we use this equation 2 in equation 1. Then it become y z d2x upon dx square plus zx d2y upon dy square plus xy d2z upon dz square plus 2me upon h cross square into yz equal to 0. Now divided by this equation by xyz. Here we divide this equation by xyz. After dividing we get 1 upon x d2x upon dx square plus 1 by y d2y upon dy square plus 1 upon z d2z upon dz square plus 2m h cross square e equal to 0. This is the equation number 3. Now the velocity of free particle can be resolved in three components. Three component means along the x, y, z, along the coordinate axis. Hence, the kinetic energy can be expressed as the sum of the corresponding term Ex, Ey and Ez. Because here the free particle is inside the cubical box, and then the velocity of this particle along the x-axis it become Vx, along the z-axis it become Vz, and along the y-axis it become Vy. It means that velocity of this particle is resolved along the three axes, and because of the different velocity along the different axes there is the different kinetic energy. Means along the x-axis it become Ex, kinetic energy become Ex, along the y-axis it become Ey, and along the z-axis it become Ez. Then the total kinetic energy of this particle inside the box become sum of these three components here. Therefore, this total kinetic energy can be written as E equal to Ex plus Ey plus Ez. This is the equation number 4. Therefore, from the equation 3 and 4, we can write here from equation 3 and 4 we can write this equation, means this total energy is resolved into the three component. Therefore, this equation can be written as 1 upon x d2x upon dx square plus 2mex upon h cross square. Only we substitute this value here and then separate the x term, y term and the z term. X component, y component and the z component. Now again the second term become 1 upon y d2y upon dy square plus 2m ey upon h cross square. Similarly the third term is 1 upon 2 d2z upon dz square plus 2m Ez upon h cross square, which is equal to 0. Then in it gives the three independent equation. Means if we separate this term, if we observe this equation, it gives the three independent equation which can be written as here d2x upon dx square plus 2m ex upon h cross square into x equal to 0. Means if we substitute this value equal to 0 and takes x equal multiply by x here, then we get this term, this equation here. Similarly, if we equate this term equal to 0 and multiply by y, then we get this second equation d2y upon dy square plus 2m ey upon h cross square into y equal to 0. Similarly, equate this third term equal to 0 and multiply by z, we get this equation d2z upon dz square plus 2m ez upon h cross square into z equal to 0. This is the three independent equation, and this equation, this three equation which is the equation 5 are the equation for one dimensional case. The boundary condition applicable to the solution are, for this equation we get this is the one dimensional differential equation in x-axis, along the x-axis, along y and along the z-axis. Then the solution for that, we get the solution of for that differential equation. Then to obtain the solution we have the some boundary condition. Here these are the boundary condition at x 0 and at x a equal to 0 and y 0 yb which is equal to 0. This 0 it means that at the boundary condition the wave function here the y at the wave function is 0. Here we define this. Therefore we can write here this boundary condition like this. Now the corresponding eigenvalues and the normalized eigenfunction are, for one dimensional we find out the eigenvalues and eigenfunction. Then for the one dimensional we can write this eigenvalues Ex equal to pi square h cross square 2ma square and x square, means along the x axis this will get the eigenvalues, and then the wave function become under root of 2 upon a sine nx pi x upon a. This derivation for energy eigenvalue and the wave function we derived in a previous lecture. Here we directly write this equation here. Here it become along the x-axis. Now along the y-axis, these eigenvalues for energy is pi square h cross square upon 2m b square. Here we get the b square because along the y-axis the length of the cube is a b. Therefore we get the b square ny square. Then wave function under root of 2 upon b here, sine of ny pi y upon b. Similarly along the z-axis again it become pi square h cross square upon 2mc square and z, and the wave function is under root of 2 upon c sine nz pi z upon c. These are the eigenvalues and the normalized wave function in a cubical box. Then the eigenvalues of the energy, we know that the kinetic energy is resolved into the three components 3x, 3y and the 3z, and we take the sum of these three terms here. Here in equation 4 we define this kinetic energy, total kinetic energy is Ex plus Ey and the Ez. Therefore the energy become here by using this equation. Then substitute this equation in equation 4, then we get this term pi square h cross square 2m square and x square plus pi square h cross square 2mb square and y square. These values, this Ey, Ez and the Ex value we substitute here 3. Then taking the common pi square h cross square upon 2m, the remaining term is nx square upon a square plus ny square upon b square plus nz square upon c square. This is the equation number 9, where nx is nothing but 1, 2, 3, 4 and so on. Similarly ny equal to n2 1, 2, 3, 4 and nz is also 1, 2, 3, 4 so on. This equation gives the eigenvalues of the energy of the particle in a cubical box. The next is a wave function. The total normalized wave function inside the box for the stationary state is given by, here it is given by, we also define the psi is the product of the x, y, z. Here in equation 2 we define the psi x, y, z is the product of x, y, z. Therefore from this equation 6, 7 and 8 we can substitute the value of x, y, z. Then it become the wave function xyz equal to, after substituting the all values from this equation 7, 8, 9, we can write this equation under root of 8 a b c sine of nx pi x upon a sine of ny pi y upon b sine of nz pi z upon c, where nx and ny are the integer. Now from this equation we clear that the energy of the particle in a box is a quantized. It is inversely proportional to the mass of the particle. From this equation, energy equation and the wave equation, we can conclude some conclusion. Among this, we can say that this energy is inversely proportional to the mass of the particle. The next is the lowest possible, the three integer nx, ny and the nz, which are called the quantum number, describe each stationary state. The lowest possible energy, that is the energy in the ground state, occur when the nx, ny, nz equal to 1 and it depends on the values of a, b, c. Then the energy is, where this energy is depend of nx, ny, nz and a, b, c. For the ground state energy level, for the ground state means nx equal to 1, ny equal to 1 and nz equal to 1. Then the energy for ground state, then substitute nx equal to 1, ny equal to 1 and nz equal to 1. Then we get the energy E equal to pi square h cross square upon 2m 1 upon a square plus 1 upon b square plus 1 upon c square. Now, if the particle is confined in a cubical box, if the particle is moved in a cubical box, and we know that the length of the cubical box along the x, y, z axis is equal, therefore we consider here the length of the cubical box along the x-axis is equal to the along the y-axis, which is equal to along the z-axis. Therefore, we write here a equal to b equal to c, which is equal to 1 here. This is the 1. Here we substitute this value 1. Then the eigenvalues of the energy are given by. Then after substituting here the ground state energy, and for the cubical box we substitute a equal to b equal to c equal to 1, or here or here in main equation we get this value. Okay, pi square h cross square 2m nx square plus ny square plus nz square. And for the ground state energy level, we know that nx equal to ny equal to nz equal to 1. Then this energy become, this is after substituting here 1 1 1, we get the 3. It become 3 pi square h cross square upon 2m here. No other state still have this energy, and this state has only one wave function. Therefore, the ground state and the energy levels are said to be a non-degenerate state. Then next is in a cubical box, the energy depends on the sum of the square of the quantum numbers. Here energy depends on the sum of the square of the quantum numbers. This nx, ny, nz are the quantum numbers. Consequently, the particle having the same energy in an excited state will have the several different stationary state, or the different wave functions. Such state are called as the energy levels are said to be degenerate. Here are the example. If we consider the first excited state value of the quantum number, here we consider the quantum number 211. This quantum number can be written as 211 or 121 or 112, means it gives the three different wave function. But if we calculate the energy for these three different wave function, we will get the same value of the energy, that is 6 pi square h cross square 2 ml square. And therefore we can say that this is the threefold degenerate state, because it has the three wave function having the same energy value, and therefore it is called as a threefold wave function. In this case, here it is the only one possibility. Here the energy state wave quantum numbers are the 111, and there is the only one possibility, and therefore it has only one wave function having only this energy 3 pi square h cross square upon 2m, and therefore it is called as a non-degenerate here. Here we define this is ground state energy is a non-degenerate, but in this case there is the three types of the wave function having the same energy, therefore it called as a threefold degeneracy. Okay, the next is the degree of the degeneracy. Now for the degree of degeneracy, we consider the number of independent wave function for the stationary state of an energy level is called as the degree of degeneracy of the level. For that we consider the particle in a cubical box of the number of energy level with the corresponding quantum numbers, and the degree of degeneracy are given in the following table. Here we consider the quantum's number 111. We know that this is the only one possibility 111, and then calculate the energy, means substitute the value of nx, ny and nz equal to 1, and it is the cubical box, means a equal to b equal to c equal to 1. Then substitute this value in a energy function, then we get the energy 3 pi square h cross square upon 2 ml square. It means that it is the non-degenerate state. A second quantum number 211, there is the three possibility, we can write these three wave functions 211, 121 and 112. If we calculate the energy for these three different states, we get the same value, 6 pi square upon h cross square 2 ml square. ml square, it means that the threefold degeneracy. Similarly for 311, we get three possibility and the energy is 11 pi square h cross square 2 ml square. Again it is called as a threefold because there is the three possibility, or the for the three different wave function we have the same energy, therefore it is called as a threefold degeneracy. Again 211, there is the three wave function and for three wave function we have the energy 9 pi square upon pi square h cross square upon 2 ml square, it is also called as a threefold degeneracy. The next is a 222. There is only one possibility or only one wave function and therefore it is also called as a non-degenerate. Now the next is a 123. This 123 has the 6 type of the wave function or can be written in having the different 6 wave function. Therefore here 123, 132, 213, 231, 312, 321. In this way we get the three different state and hence the in this way we get the 6 different state and hence get the 6 different wave function having the same energy for 14 pi square upon pi square h cross square upon 2 ml square. Therefore it is called as a 6-fold degenerate. This is the degree of the degeneracy. In this way we can find out the different quantum number having the energy and the degree of degeneracy. Now next is the numericals. Here is the numerical. The first numerical is find the lowest energy of an electron in a cubical box of each at which the average energy of the molecule of the perfect gas would be equal to the lowest energy of the electrons. Here K is given. Here K equal to 1.38 into 10 to the power minus 23 joule per degree Kelvin. Mass of electron is here 9.1 into 10 to the minus 31. The length of the sides of the cube, we know that here is the cube, therefore we have the side A equal to B equal to C, and which is 1 angstrom in it, which is nothing but the 10 to the minus 10 meter, and the Planck constant H equal to 6.63 into 10 to the minus 34 joule second. We have to find the lowest energy. Lowest energy means ground state energy means 111, and it is given by, here we write this formula, pi square h cross square upon 2m. In bracket we get the nx square upon a square plus ny square upon b square and plus nz square upon c square. Now for the lowest energy, nx equal to ny equal to nz equal to 1 and the length of the side is given here. Then substitute all value. Here h cross, here h is given, therefore this convert into the h cross. This become h square upon 8ma square. After substituting the h cross equal to h upon 2 pi value, here we get this value, and here 1 upon a square, 1 upon b square, 1 upon c square. Then a, b, c equal to 1. Then we get the 3 h square upon 8 ma square. Then we have substituted the value, mass, not a square, 8. Then substitute the value. Here we get the lowest energy, and the next is the also find the temperature at which the average energy of the molecule of the perfect gas. The average energy, for the average energy is a 3 by 2 kT, okay, which is equal to lowest energy, this energy. After calculating we get this energy or the value of this energy. Here we substitute this energy. Here K is given. Here K is given. We have to only calculate the T. Then by using this formula we can calculate the energy. Here is the end of the second unit.